Hello everyone, welcome back to another physics lesson. I'm Physics Michael and today we're going to explore a really important topic, motion equations. These are often called the so what equations. So we will start with describing motion with so what, then derive the equations through weighted graph and solve some questions with the equations. Alright, let's jump right in. First, let's review what uniform acceleration means. Uniform acceleration happens when an object's velocity changes at a constant rate. In other words, the amount of velocity changed is the same in each equal time interval. Now, let's look at the velocity time graph. If the graph has a straight line with a constant slope, that means the object is accelerating uniformly. For example, this graph here shows uniform acceleration, and so does this one. But this third one, its slope is changing, so that's not uniform acceleration. Next, let's look at how we describe motion using some key physical quantities. Imagine a car accelerating on a straight road. We use the letter U to represent its initial velocity and A for its acceleration. After a certain amount of time, which we call t, the car covers a displacement labeled as s and reaches a new final velocity which called v. So we have five quantities s, u, v, a, and t. We spell out the acronym so what. The motion equations are formulas that link these five quantities together. Now, let's try deriving these equations one by one using a velocity time graph. We start with the definition of acceleration. Acceleration is the change in velocity divided by the time it takes for that change. So we can say acceleration equals to final velocity minus initial velocity and divided by time. Rearranging that gives us final velocity equals to initial velocity plus acceleration multiplied by time. This is the first motion equation, and it tells us how fast an object is going after a certain amount of time when it is accelerating uniformly. Now, let's find a formula for displacement. On the velocity time graph, the area under the graph tells us how far the object has traveled. That's displacement. The area under the graph is shaped like a trapezium or trapezoid, so we use the trapezium area formula. That gives us displacement equals to the sum of the initial and final velocities divided by 2, then multiplied by time. That's our second equation, useful when you know the starting and ending velocities. And by this equation, we can find that the average velocity is just equal to the sum of the initial and final velocities divided by 2. Now, let's use the first two equations to get the third one. Start with the first equation, final velocity equals initial velocity plus acceleration times time. Now, substitute v into the second equation. After simplifying, we get displacement equals to initial velocity times time plus 1/2 of acceleration times time squared. This is our third motion equation, very helpful when we know the initial velocity and acceleration at the time, but not the final velocity. Next, let's find an equation that doesn't involve time at all. Start again with the first equation and solve it for time. Then substitute t into the second equation and simplify. In the end, you get final velocity squared equals to initial velocity squared plus 2 times acceleration times displacement. That's the first equation, and it's great when we don't know or don't need the time. So now we have all four motion equations, also known as the so what equations. Remember, these equations only work when acceleration is constant and the object is moving in a straight line. Also, the letter s, u, v, and a are vectors, so direction matters. We usually use a positive sign to represent one direction, like to the right, and a negative sign for the opposite direction, like to the left. For example, if a car is moving to the right with an initial velocity of 4 meters per second, we say positive 4. If it accelerates to the right at 5 meters per second squared, we write that as positive 5. But if the car accelerates to the left instead, we call that negative 5 meters per second squared. Let's try solving a question using the so what equations. A car is moving at a constant velocity of 10 meters per second, then starts speeding up with a constant acceleration of 2 meters per second squared for 5 seconds. What is its velocity after 5 seconds and how far does it travel? We will solve this in 3 steps. Step 1. Write down what we know. Initial velocity is 10 meters per second. Acceleration is 2 meters per second squared. Time is 5 seconds. We need to find final velocity and displacement. Step 2. Choose the right equations. We use the first equation. Final velocity equals initial velocity plus acceleration times time to find the new velocity. We use the second equation, displacement equals initial plus final velocity divided by 2, then multiplied by time to find how far the car travels. Step 3. Solve. Final velocity is 10 plus 2 times 5, which equals 20 meters per second. Displacement is the average of 10 and 20, which is 15, times 5 seconds. That's 75 meters. Let's try another example. A car is driving at 30 meters per second. Then it starts braking with a constant deceleration of 5 meters per second squared. After traveling 80 meters while braking, what is its new velocity? Again, we follow the same 3 steps. Step 1. Write down what we know. Initial velocity is 30 meters per second. Acceleration is negative 5 meters per second squared because it's slowing down. Displacement is 80 meters. We don't know the time or the final velocity. Step 2. Choose the right equations. Since we don't know the time, we use the fourth equation. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Step 3. Solve. Initial velocity squared is 900. 2 times acceleration times displacement is negative 800. So final velocity squared is 100. Taking the square root of that, the final velocity is 10 meters per second. Let's wrap up with a quick summary of what we've learned today. 1. We can describe motion with constant acceleration using 5 key quantities: displacement, initial velocity, final velocity, acceleration, and time. Remember that S, U, V, and A are vectors, so direction matters. Use positive and negative signs. 2. We can use velocity time graphs to derive 4 motion equations that describe how these quantities are connected. 3. When solving problems, always list the known and unknown values and pay attention to the directions. Pick the right equation and then solve step by step. That's it for today's lesson. Thanks so much for watching. I hope you now feel confident using motion equations and solving these types of problems. I'm Physics Michael, and I will see you in the next video.